Hello, everyone. This is the first official podcast for Matter and Meaning, where we interview people who try to find meaning from the matter of the universe. I will be
Mhm.
your host, Jack. I will be doing most of the video editing, and I will also be doing a lot of outreach trying to get people on the podcast. And would you like to introduce yourself?
My name's Ben. I'm in charge of the audio, and I'm also going to be interviewing where I can. So yeah, I'm very excited for this new podcast. Should be very cool.
Yeah, it's been really nice to get your input on some of the interviews that we've already recorded, actually. I like
Yeah.
the one that we're about to show after this introduction clip is one where I thought some of your questions were really good, and I quite
Hmm.
enjoyed that conversation with Sarah. But
Hmm.
anyways, our goal with this podcast, even though this is kind of a continuation of the physics podcast from before, this is still a physics podcast, but our goal is to make it accessible to all levels of listeners. So whether you're a master's student or not even in the physics department, you can enjoy the content that we're putting out. We want everybody to be able to understand it, right? So we're going to go over some advanced topics, but we're going to start from the ground up whenever we go over that stuff. And
Hmm.
we're going to go over stuff that's mentally stimulating for all levels of listeners and hopefully just something that you can kind of put on in the background as well and just, you know, find some good keywords. We also want to be a keyword source.
Hmm.
So yeah, we're gonna be based pretty much on just interviewing people. So every podcast will be interviewing people, professors from Swansea University, which will hopefully strike some like curiosity in the physics department, where if they thought something was interesting from the podcast or it made them have a question, they can go up to the professors that we interviewed and ask them interesting questions and insightful questions. Um,
Hmm.
We'll also be interviewing people from the industry. So we have some people from Stanford Linear Accelerator. Hopefully, fingers crossed, we'll be interviewing somebody soon who used to research at Oxford, and also have some people from Apple and Google that we'll be interviewing, kind of just to give students a sense of what they might want to do with their degree. Maybe they want to change majors for their master's because that aligns with something that they might want to do in the future, what kind of stuff you should be doing extracurricular wise as well, and what like a normal career path looks like for somebody who's done physics or chemistry or a STEM subject like that. And yeah, that's pretty much everything, all the information about the podcast that we want to get out there before everybody listens to the first one. Do you have anything to add at all?
No, I think you've covered everything. I think we should just start the podcast and get into the interview.
All right. Okay, guys. Well, I hope you love this first interview. I think this was one of my favorites to record so far, so hope you guys like it as much as I liked talking in it. And we'll see you guys in the next interview. See you
Hmm.
later. All right. Hello. I'm Jack, the main podcast host. I'm also here with
Ben, I'm kind of the technical guy, but also I like asking questions. So yeah, I thought I'd like joining on the podcast as well. Yeah,
and
we're here with Sarah Roberts,
yeah.
who is the mainly I'd say like astrophysics whiz of the department.
Oh, I like that
I like that.
title. Yeah, yeah, that's better than lecturer. Yeah, I'll take that.
We'll go with that.
Yeah, I'll take that. Yeah.
All right, so let's start off with the questions then.
Okay.
You've gotten your PhD. What was the PhD about?
Yeah, flipping out. My PhD was so long ago. Let's see if I can actually remember. No, my PhD was looking for dwarf galaxies in different parts of the universe. So a dwarf galaxy, as the name suggests, is a smaller galaxy than like our giant Milky Way galaxy that we live in.
Mhm.
They're faint, so they're really hard to find. And the reason that I was looking for them was because according to the standard model of how how structure forms in the universe, so that's what they call the lambda CDM model. We can talk more about that after. Dwarf galaxies should be the first type of objects that form first in the universe. So small objects form first, and then they merge together to form bigger objects. So just like if you were building a house, and you build a house with bricks, and if you go to like a building yard and you have all the houses, so that's the big galaxies, you'd also have leftover rubble in a building yard. So you'd expect to see leftover dwarf galaxies as well. that's what the theory said. That's what it predicted. But observations, up to when I was doing my PhD, didn't find the number of dwarf galaxies as they expected. They found too few. So a big part of the reasoning behind doing my PhD was to see whether the theory was wrong or to investigate whether something else was happening in the universe to stop dwarf galaxies being found.
Sure.
Yeah. So basically I did the observational side. I didn't do simulations or anything like that, but obviously I had to take them into account. So I had to travel to lots of exotic places to use telescopes. It's such a hard life. And I took lots of observations of different parts of the universe, like clusters of galaxies or groups of galaxies, and then empty space, not quite empty, but just around single galaxies. And then I looked through data to see if I could find any dwarf galaxies and see if I could discover any new ones and see whether that could match up with the number that were predicted by theory.
Mm-hmm. So when you're looking through the data, what kind of things are you looking for, which would be a telltale sign for a dwarf galaxy?
Blobs, literally blobs. They are fuzzy.
Anomaly kind of thing.
Yeah. So when you're looking at the data, so you have your like star field or whatever, and it's literally like someone smudged something on the screen. Because a dwarf galaxy, or the ones I was looking for, are also low surface brightness, which means that they're not really bright in there. The light is very spread out. So they literally, it's a bit like a globular cluster, but if you imagine if that was even fainter with the stars spread even more spread out, it's just really faint and just like a slight overdensity of stars in there. So I literally spent hours and hours scrolling through lots of images to say, okay, yeah, that looks like a dwarf spheroidal, or that looks like a dwarf irregular, and just categorizing them like that. It was great. It was.
Sure. All right. So getting through an undergraduate and then going on to do your PhD after is some pretty serious work. So what was some stuff that kind of motivated you through that?
Okay. Well, so when I was doing my undergrad degree, I really enjoyed it. I did physics with astronomy in Cardiff Uni, and I really loved the astro side of it. I mean, who doesn't love astronomy anyway? But I have to confess that it wasn't necessarily my main aim to do a PhD afterwards. As I was getting to the end of my degree, so I did an MPhys, I didn't really know what I wanted to do. And I went to speak to some of the PhD students in the department at the time, and I can remember them saying to me, "Don't do a PhD, Sarah, don't do it. It's hell on earth." And I was like, "Oh, it can't be that bad because you're doing it." And they were like, "No, really, don't do it." And I was like, okay. So I applied for some PhDs. I wasn't successful, and I thought, fine, I'll take a bit of time out and I'll just get a job. So I got a job in the job centre, ironically enough, helping other people get jobs. And then I applied for a job with the British Antarctic Survey. So I was waiting to hear back from them. And then I heard that there was money left in the department in Cardiff for a PhD place. So I went in to talk to the person who was in charge of the money, and he explained about the project and all about trying to find dwarf galaxies and stuff. And I thought, oh, that sounds cool. And I said, oh, yeah, I'd like to do that. And he was like, yeah, okay, fine. Because that's how it worked back then. So that's how I got it. And then actually I was phoned up then I was offered the British Antarctic job, but turned that down because I was already doing my PhD. So, yeah.
So now that you've finished your PhD, do you feel the same way as those other people telling you never do a PhD?
No, I do understand what they were getting at. Because they were saying unless you're really, really passionate about it, it's really hard work, and I don't think people realise just how hard work it is. But if you are passionate about it, and if you should be interested in the topic, otherwise you shouldn't be doing it, then it's not as bad. But yeah, there were some times during my PhD that I did think to myself, oh, why are you doing this? But they were few and far between, and I did really enjoy it, and I got to travel loads, and it was really interesting. And as I was writing up, I was thinking, oh, this is great bringing it all together. So it was a lot of hard work, but definitely worth it for me anyway. It's not for everyone, but I enjoyed it. Yeah. And it got me where I am now. So yeah, that's good.
Yeah. Okay. That's super cool. So it wasn't your main intent to go into a PhD?
No, to be honest, I didn't really have a clue what I wanted to do. And we didn't really have a lot of careers advice when we were getting towards the end of our degrees. So I didn't really know what sort of things I'd be interested in doing and what sort of things were out there anyway. So it sort of fell in my lap, which is good. But obviously, I think we've got a lot more. We help students a lot more with careers and stuff now. It didn't seem to be the case back in my day. But yeah, it worked out well. So
sure. A couple of weeks ago, me and Ben were talking with Alad Isaac after a lab, and he said, which I thought was actually quite interesting, that it wasn't originally his intent. He kind of like fell into the position of teaching at a university, and that kind of got me thinking, how often does that happen? Because it's a very rigorous thing to be teaching physics at a university. So what kind of got you into that scene then?
So when I finished my PhD, when I got to the end of it, as I say, I really enjoyed it and I was glad that I did it. But at the end of it, I knew I didn't want to carry on in research. They were just, it wasn't the politics of it, but I don't know whether it was our area or whether this is true for all areas. There seemed to be a lot of sort of infighting and stuff. And I thought, oh, do you know what? That's not really for me. But as I was finishing writing up my PhD, a project called the Fawkes Telescope Project, which was an outreach project, came to Cardiff University, and I actually got a job with them because through my PhD, I had been I'd been a lab demonstrator and I'd been doing lots of outreach and public engagement as well. And I really, really enjoyed that. And I loved going into schools and talking to little kids about space because they get very excited. So I started working for them. And through them, through the Fawkes Telescope Project, I actually got I became an hourly paid lecturer on an astronomy course up at the University of South Wales, which was University of Glamorgan then. And I realised that actually I really enjoyed teaching, probably because I like the outreach and public engagement. I know teaching is different to that, but I realised that I liked explaining things to people and seeing that sort of spark of, oh yeah, I understand that now if they didn't understand something before. So when I started doing that, I was very keen to carry on teaching then because I knew I didn't want to carry on with research. I thought, okay, well, then I'll go into teaching.
Do you briefly explain the Fawkes Telescope Project? Because I know we've kind of briefly known about it from doing the course, but some listeners that might not understand what it is. It's quite an interesting project.
It is. It was.
And you're still involved with it as well.
Well, right. So let me explain it first, and then I'll explain what's happened to it. So, the Fawkes Telescope Project was an educational program that aimed to get young people in schools interested in the STEM subjects, so science, technology, engineering, and maths, using astronomy as the hook. So with that, we had a network of telescopes around the world that school children could access, they could control, and they could take any images that they wanted to. And so I was the director of education for the Fawkes Project for, oh my gosh, I don't know, like 20 years or something like that. So I started off just writing sort of observing plans for people and giving advice and everything. And then I ended up sort of doing teacher training and running the education programme. But as of last year, I think it was, the Fawkes Telescope Project was taken over by in a nice way, not a hostile takeover. It was taken into the Schools Observatory Project, which is a very similar project where they do education for schools with using robotic telescopes. They had one telescope in La Palma, the Liverpool telescope. And so they basically took the Fawkes Project and all the telescopes and resources and everything, and it's been merged into one.
Okay.
because they've actually got a team of people who get paid to do it. So although when I started working for the Folks Project, I was paid, eventually the funding stopped and we were all doing it just as a part of our other jobs, which was like lecturing or whatever. Yeah, it was a passion project, basically, yeah.
Okay.
It was a great project as well. And it's, as I say, it's still continuing with the Schools Observatory. So kids, children or pupils in school can still use the telescopes and do astronomical research or just take pretty pictures or whatever they want with the telescopes. But it's under the Schools Observatory banner now.
Okay.
So.
Kind of going back to what you were bringing up before about how you enjoyed outreach and eventually that led you to really enjoying teaching. Do you want to talk a little bit about something that I thought was quite interesting about one of your, I don't know how to explain this properly. I heard that you gave a lecture to a prison.
I have been in prison, yes. So one of the projects that I was invited to be a part of was one that was funded, and it was essentially to try and do an astronomy series on National Prison Radio. So I was invited to Leicester Prison with a panel of other experts. I was an expert. So there was a panel of us. There were, I think, about 4 or 5 of us, each sort of an expert in different area of astronomy. And we were there to talk to, there were about 6 inmates that we talked to. So they were sort of interviewing us a bit like you're interviewing me now.
It was also on the radio.
And it was the first ever science show that they'd ever broadcast on National Prison Radio. And they wanted to do an astronomy one because they said that there was a massive interest in astronomy and loads of people would listen to it. And it was really well received as well. It was good. It was quite an experience. Like beforehand, obviously we were sent lots of information about what we could and couldn't take in with us, what we could and couldn't sort of like wear in our hair and stuff like that. Because obviously they think, well, you have to be searched when you go in because you can't smuggle things in, and just have to make sure that you've got nothing on your person that can be used in any way that it shouldn't be used and that. But it was, we were just all sat in this room. They were sat over there, we were sat here, and they were just asking us questions. It was cool. It was really nice. And one of the inmates felt really bad for him because he wanted to be a teacher. He was so interested and he knew so much about astronomy and he really wanted to go into teaching. But obviously with the criminal records, you wouldn't be able to do that, which is a shame because I think he would have made a great teacher.
Yeah, I do think astronomy is probably one of the best ways to get people interested in science.
Yeah.
It doesn't matter what age you are. It's like I use like Brian Cox as a good example. Like you watch a video about when he's talking about space, and I have never met someone that watched a video like that and doesn't say like it's really interesting.
Yeah.
Doesn't start a conversation.
Well, in one of the things that I used to do, I used to teach GCSE astronomy to local schools in like the South Wales Valleys region, so they were quite deprived schools. And one of the schools I went to, I was just teaching girls because they were trying out a program to try and get girls interested in science. And I can remember one of the girls, she was like 13 or 14, in one of my lessons, saying, "Oh, Miss, I hate science." I was like, "Oh, you're not enjoying our astronomy class?" And she was like, "Oh, yeah, no, I love this." And I was like, "You do realise that you're doing science, don't you?" "Oh, yeah." And it was just like, this is science, but he used astronomy as the hook, and loads of people get excited about that. Yeah.
It seems a lot of like science in school, especially, I remember being quite dry, and it definitely doesn't seem. There's like special topics that you do, but a lot of times it's just like you're learning. It's like,
well, that's why
how is this going to be useful? And that kind of stuff. It's really important to have like obviously these outreach projects, the kind of stuff that you've done in the past.
That's why the Folks Project was started because Dill Fawkes,
it's like his hands-on.
experience. He gave £10 million of his own money to build a telescope in Hawaii and a telescope in Australia, and it was specifically to try and engage young people in like maths, physics, all the sciences, because he saw that actually the way that science is taught in a lot of schools was quite dry and wasn't really that interesting. So if you could do something to get people interested in it, then why not use a £5 million telescope in Hawaii and do that?
Yeah, if you've got the money to spend on it, it's
exactly.
It's only worth it to spend it.
Yeah, exactly. He had lots of money, so fair play to him.
Yeah, I definitely had very dry experiences learning chemistry and biology in my school. I never got very good grades in any of my science classes either. I feel like they could do a lot better of a job teaching young people science and getting them exposed to the right things at the right ages.
Well, the reason that I chose physics, so when I was doing my A-levels, I wasn't sure whether to choose A-level physics or A-level biology. And so I thought, okay, well, I'll do the two of them for now, and then I'll drop one because I was doing maths and chemistry as well. And the first A-level biology lesson I went to, they were talking about plants. I thought, oh my God, I can't stick 2 years of plants. So I dropped that. And the physics one, our teacher, she was absolutely amazing. She was quite crazy, but she was crazy in a good way. She was really good, enthusiastic. She let us choose what sort of modules that we wanted to do. So we all chose astronomy. So that's probably, that is definitely why I chose physics, because she was so passionate about it. And she made it really interesting. She did try her best to make it interesting. So, makes a difference.
Yeah, for sure.
Yeah.
I think the kind of teachers that you have definitely play a big role in like what you end up choosing to do.
Definitely. You can be put off a subject for life with the wrong teacher. You really can.
Yeah.
That's definitely how I was with biology. I've never looked back. I was like 13. Never want to talk about biology again. But I quite enjoyed my physics teacher. So
see, if we'd have started with dissecting some animal part, then I don't know, I might have been a biomedical scientist or something. But
there's interesting parts of every subject.
And some people probably love plants, so I'm sure plants are very interesting, but they just weren't for me. I just needed the E in there, turn it to planets, and then I'm sorted on. See what I did there? Yeah, thinking on my feet.
I remember in school, like one of the most asked questions, especially in maths, I think, was like, "Oh, when is this going to be useful, like in the future?" How do you answer a question like that to a student?
Well, if they were talking about maths, I'd say maths is everywhere.
Yeah.
How else are you going to know whether you've got enough pocket money to buy whatever you need to buy? I mean, that's just basic maths. I'm trying to think of how else I'd...
Like a path integral or something. I heard that they use that in economics. Stocks in the stock market and stuff.
Yeah.
So...
Yeah. And it also depends, because you don't know, like when you're in high school, you don't really know. Well, a lot of people don't know what they want to do. Like I didn't know what I wanted to do. I thought I might go into archaeology, and then I ended up nowhere near archaeology, really, unless you count looking back in time in the universe. I don't know. But yeah, I'd say you don't know what you don't know what's going to be useful, because you don't know what your future is going to hold and what you decide to study. It's a good question.
Well, the reason I ask it is because I see a lot of similarity in when students ask that versus when like people that fund projects, for example, they ask like things that we learn about now, like dark matter and dark energy, for example. Like a lot of people say, "So what?" about those kind of things as well.
Yeah.
Like, how is this going to like actually benefit humanity? It's just sort of like we will know it, and then we'll be like, okay, now we know it, and we're just like more intelligent.
Yeah, but with that,
it might actually be useful.
I mean, it is great, sort of extending our knowledge and finding out, what is the universe made up of and everything. But it's not just that; it's all the steps in between and all the technology that you have to develop for that, and that technology then has spin-offs. Like, I don't know whether it's true or not that Velcro was invented for space, basically, but I mean, we use Velcro all the time now. Teflon as well. So it's not just the knowledge that you're gaining, but it's all the stuff that you... Yeah, exactly.
Well.
Yeah.
Sure.
Yeah.
So speaking of dark matter, I feel like that's a good segue into... Would you like to explain the basics of the lambda CDM
lambda
model?
CDM model.
Yeah.
Okay, yeah. So this is the standard model of how the universe, not how it began, but basically how structure formed in the universe. So it's like the current accepted theory of like we have the Big Bang, we have the Big Bang, we have so the lambda part just shows that there's a cosmological constant, so that's to do with the acceleration of the expansion of the universe, and then the CDM part is cold dark matter. So it's the type of dark matter that the universe is made up of. And it's not to do with the temperature of the dark matter, it's to do with how much energy it has. Because essentially, when the universe began, you have like density fluctuations early in the universe. And so depending on how those density fluctuations grow, so you'll get some overdense regions and you get underdense regions. And depending on the type of dark matter that's around, you'll get different size or different scale size objects forming. So with cold dark matter, that's when like the particles have low energy. So actually you can have, it means that smaller objects form first. And so that's what we would see as dwarf galaxies forming first, and then larger objects would merge together on top of that. If you had hot dark matter, then the particles in that sort of scenario have more energy. They move at speeds close to the speed of light. So they'd actually wash out any smaller sort of fluctuations. So bigger objects would form first, and then they would break down over time to form the smaller objects that we see today. And then you have the intermediate, always have the intermediate warm dark matter, which is a mixture of the two, basically. But any theory that you have of how structure forms in the universe and any model of dark matter that you have has to explain all the observations that we see. So that's why theory and observations go hand in hand. So with the cold dark matter theory, or lambda CDM, that obviously gives predictions for what the cosmic microwave background should look like the fluctuations in it, but also so from the smallest things to the large scale structure that we see. So how galaxies sort of are presented with filaments and voids and galaxy clusters and superclusters and things like that. And they do. So the lambda CDM model does explain that really, really well. But it does have some problems, like the fact that it predicts lots of dark matter, lots of dwarf galaxies. It's called a missing satellite or missing mass problem. So there are some things that it doesn't quite agree with, but at the moment, it's the best theory for how structure formed.
Okay. Now, this question, I'm not really sure if this is like, there's going to be a clear-cut answer to this, or this is just something that...
Probably not if it's astronomy.
well, I don't know. Well, because this also goes outside of your area of expertise, so I was just curious about this because I heard it on the internet. So
if it's on the internet, it must be true.
It has to be. It has to be.
Sort of Facebook post.
Exactly. No, I heard that the lambda CDM model is pretty much like, if you were to compare the two, the same thing as like the standard model of particle physics, but for cosmology. Like that's the amount of importance that it has for the field.
Yes.
Is that a fair comparison?
Oh, definitely. Yeah.
Okay.
Yeah, because it is about basically how the universe began and how things formed in the beginning. So you have stars and then you have dwarf galaxies forming and merging together. So it is that important, which is why, astronomers, astrophysicists do a lot of work on doing the simulations, but then also obviously doing the observations as well. Sure. Because then you can go into, and this is not my area of expertise, so don't ask me any more about this, but there is something called MOND, which is modified Newtonian dynamics. So there are some schools of thought that say that we don't need dark matter at all, and that actually we just need to revise our theory of gravity and how gravity behaves and affects things as well. But,
is that a relatively new theory? Or
no, that's been around a long time. Yeah. Thing is, that was around definitely when I was doing my PhD, and at that time it was a bit like a fringe thing. And if you thought about MOND, you were like a bit on the edge, and people didn't really think weren't that respectful of it. But I think it has actually grown a lot over the recent years. I don't know what the status of it now, but it's definitely a bit more mainstream than it used to be. Yeah. It's probably other people in the department who can talk about MOND, maybe.
Really?
Possibly.
Yeah.
It's worth asking.
Yeah, that's the first time I've heard about that.
Is it? Yeah. You probably go on the internet now and say, MOND is absolute nonsense. It won't. No, there's definitely, because that can explain some of the things that were discrepancies between the CDM model and what was observed. That explains some things, but it couldn't also explain like the CMB fluctuations and how large-scale structure appeared in observations. Yeah. So, it's, it might, who knows, might be a mixture of the two. I don't know. That's for your generation to find out.
Yeah.
Yeah.
That's the thing.
Yeah.
Yeah. It does seem a lot of theories, and they can explain some things really well, and then other things it's like it kind of breaks down.
Yeah. But I mean, with my area, so looking for dwarf galaxies, actually, like when I started that many years ago, like 20 plus years ago, and then some, technology wasn't as good as it was now again. So even recently, even like in the past year, new dwarf galaxies have been discovered around our Milky Way galaxy.
Yeah.
And so it could be that the discrepancy between the predicted number and the observed number, some of that is definitely down to the fact that we didn't have good enough cameras to actually see really faint, fuzzy objects in the universe, because they were just too faint for us to collect light from them. And now we're actually seeing more. Although in some cases we're actually seeing too many dwarf galaxies than is predicted. So it's gone the other way. So it's just, things will always need tweaking.
Yeah.
Whether it's theories or
especially
advanced.
when it's because a lot of these things are like we're only just, like you said, we're only just starting to discover them and be able to see these kind of things.
Exactly. I don't think we'll ever have all the answers.
Data. Do you think we'll ever get a unified theory?
It's a very
oh my gosh! I have no idea.
There's a guy called David Deutsch, I think.
Yeah.
He tried to like bring together a lot of different ideas. And like he kind of said, like, this is our current theory of everything based on like different strands of different parts of science and like human understanding and that kind of stuff.
I don't know.
It's probably quite a difficult thing because there's so much complexity in the universe.
Yeah, exactly.
Like, how do you explain everything? A lot of there's always been something that will.
Does it make sense that everything can be explained in one big theory?
Yeah.
I don't know.
Well, I feel like at a certain point it kind of becomes, because you can always, no matter what answer you get, you can always ask why. So there's going to be a certain point where you just
kind of
can't
becomes philosophical more than actual science.
Yeah. Oh, yeah. I mean, that's where the line goes. Right? That's kind of what we first started talking about when we didn't know each other that well. Like the similarities between philosophy and physics is it just, when you get to a certain point,
if you haven't got data to back anything up, then it's conjecture, and then it's just philosophical at that point.
And I feel like
that's
a lot of
the premise of the idea.
A lot of the stuff nowadays, I mean, maybe not even nowadays, things like string theory. Now, I don't know that much about string theory, but I feel like a lot of the stuff with advanced kind of physics models is more of like a mathematical exercise than physics at a certain point.
Yeah. You know? No, that's true.
Yeah.
Definitely.
Where it's just kind of like, it's pretty much just like philosophy at that point, because you're not really basing it off of observations and this and that. Like you can, like, maybe string theory isn't the best example for that.
Yeah.
Because I don't know
how
explanations, but
yeah,
I feel like a lot of it can just be boiled down to like, why do you think a lot of physicists get field medals and stuff instead of Nobel Prizes?
Yeah, they need to be able to make some hard predictions and say, okay, this is what you should be able to see and measure, and then you get the practical astronomers or astrophysicists, whatever, the observational astronomers who go out and actually try and find that or not find it, whichever.
Yeah. I mean, both are just as good.
Well, exactly. It still gives you an answer or some sort of answer. until technology advances, and then just gets more questions. But
Yeah.
See, this is why everyone should be studying astronomy. You'll never find the answers. There's just loads more questions.
Yeah.
It's just cool. It's like a giant detective story, but with
I've got. I was watching a video the other day about hypothetical planet 9 in our solar system. I don't know if you've heard much about it.
No.
Because they've observed some slight discrepancies in some of the orbits of the planets in our solar system. I think that's the premise of it.
Yeah. Okay.
And they can be explained by there being another planet. It's I think it's a rocky planet bigger than the Earth, but on a really 25,000 year orbit. I think it was around the sun.
Oh, okay.
And I don't know. I only watched the video. I didn't go into the references or where he got the information from and that kind of stuff. But there's a new telescope that's coming called the Rubin Observatory in Chile, which they said would be able to tell us if it exists or if it doesn't exist. But it seems like there's a lot of evidence suggesting that there could be a planet out there in the solar system.
Yeah.
Well, you never know.
I just found it really interesting. But this Rubin Observatory, because it can take a really high definition picture of the entire sky, every 3 days.
The Rubin Observatory is going to revolutionise astronomy, definitely.
Yeah, because it'll be able to. It's nearer Earth objects that it'll be able to discover. I think, isn't it?
Yeah.
Is that the digital camera?
The solar system and that kind of stuff.
That's that.
Yeah.
Named after Vera Rubin, who was a female astronomer who did loads of work on dark matter. In fact, it all comes back to dark matter. You see. Yeah. No, she was. Funny. Yeah, she did loads and loads of studying on it. So I think it was postulated or discovered originally by an astronomer called Zwicky, but Vera Rubin did loads. She spent, I think, most of her career studying dark matter in our galaxy and other galaxies. So she was the one who sort of pushed the whole sort of field of dark matter. But I think Zwicky probably got some prize for it.
Mm-hmm. So dealing with the lambda CDM model for a lot of your PhD, it seems there are a couple main candidates that we have currently for what we think dark matter might be, and something that me and Ben both know about because I saw it on his notes. I've also done some research in the past about it. Is WIMPs, WIMPs, weakly interacting massive particles. Do you have
I have absolutely no idea what dark matter is.
Okay.
Absolutely none.
I mean, that's pretty much what my question was.
Yeah. No.
Does anybody?
No. Although I'm sure if you asked some people, they would have very strong opinions one way or the other.
Sure. It's all conjecture.
It is. It is at the moment. But I think WIMPs are the best candidates, for that it's going to be particle in nature.
Sure.
If it exists.
Mm-hmm. Yeah. Oh, I did have a question about dwarf galaxies. How do you actually define a dwarf galaxy if it's orbiting a bigger galaxy? How can you look at something and say that is a dwarf galaxy rather than just a group of stars?
Oh, that's a nice question. So, what is a galaxy if not a grouping of stars? Actually, a galaxy by definition is a grouping of stars, gas and dust, and dark matter.
Okay, so it's not to do with its orbiting something.
No.
That's the only definition.
Yeah, the definition of a galaxy is it's got stars, gas, and it's embedded in a dark matter halo, essentially.
Okay. And that's something that's been observed as well at dark matter halo.
Yes, because
I've seen a picture. They had it's a purple kind of. I can't remember. I think
you can't directly observe
they assigned a color to it. Obviously.
Right. Okay. So they've So what you do is you look at the stars.
The gravity.
Yeah. You look at how fast the stars are orbiting around the center of the galaxy, like the ones towards the edge.
Yeah.
And you compare that to how fast you think it should be moving if the only mass that was in there is the mass that you could see, like the light mass, and they're actually moving faster than you think, which shows that actually there's actually dark matter. There's mass that you can't see directly in that galaxy. But a dwarf galaxy, definition is one that is, I mean, people have slightly different definitions, but basically it has a mass that's about 10 to the 6 solar masses, so 1 million times the mass of our sun, and it normally has an absolute magnitude brightness of between -10 and -14, or less, or fainter than that. Yeah, very precise definition.
Yeah, it does seem. I don't know. I was just thinking about like yesterday, like the categorizations of different things, and it's like
it's quite arbitrary.
Yeah, it does seem.
Do you
think sometimes it's maybe not beneficial to have to categorize everything, because then you get something that's like, oh, this doesn't fit in a category that.
Yeah.
I guess that's kind of useful, because it's like then it makes you think about whether like your current theories are actually correct.
Yeah, exactly.
But having such like rigid categories that are just based off of like observations.
I think as long as everyone who's using the categories understands them, then that's fine, because it's useful in a way. So when we were writing all our papers in our research group, we defined a dwarf as, okay, it's got an absolute magnitude between -10 and -14. So that was fine for us. And then we published papers. So if somebody wanted to do a similar study or compare their results with ours, knowing what our category was, they could categorize their stuff in the same way, and they can compare like with like then.
Yeah. So it's useful to make comparisons.
But you're right. Some things don't fit into these nice, neat boxes. Like when you're talking about galaxy classification, you get things which are always in between, or they look completely different, which is great. But I don't know. I think it's a human thing. We just like to categorize anything. Just put things in boxes, and like to be neat, but. Yeah, the universe doesn't really work like that.
Well, no, I was just okay. I know this isn't like exactly. This is not in your area of expertise at all.
Oh God,
it's not good. I wanted to add on to something. This is like not productive to the podcast whatsoever.
No, go on.
But talking about
cut this out then.
Talking about like categories and stuff, and how like Pluto was demoted, right? From a planet to a dwarf planet.
That's a good example.
No, it wasn't demoted. It was reclassified. It's not a demotion to be a dwarf planet, is it? Why is that a demotion?
Was it reclassified because we changed our classifications, or because we found out more data about the size of it?
It was because I don't know whether they like tightened up the rules of what a planet should be.
When did they discover the other 4 planets in our solar system? I think that
they were classed as asteroids.
Oh, were they?
They were classed as asteroids.
Okay.
Yeah. So I think
they kind of created a new.
I think they created a new classification for planets because, though I think it was because Pluto didn't quite fit the description like the other planets, because it hadn't cleared its orbit. It was still in like quite a rubble-strewn orbit. Yeah. That was one of the main ones. Yeah, and well, it is spherical. The others are spherical, but that's the main one, that it hasn't cleared its orbit, so it hasn't got enough of a sort of gravitational pull, I suppose, to clear its orbit. Yeah. So that's why they were like, okay, well, all the other planets have done that. Pluto hasn't, so let's make a new category. And then they were like, oh, well, actually, there are these other objects which are spherical, but haven't cleared their orbits. They're in the asteroid belt, so Ceres and Eris and Haumea and Makemake, I think they're the other ones. Yeah. So they have to be reclassified. So in your terminology, they've been promoted. But I just say reclassified, because there's nothing wrong with being an asteroid.
That's a very human thing to think about things being better or worse.
Yeah, but
it's like based on our classification.
Exactly. But people felt really strongly about Pluto.
Yeah,
I mean, they buy the T-shirts and everything. It's like, but why? It's still there. It hasn't moved, hasn't changed.
It doesn't even know that we've classified it.
No, it doesn't. Yeah. Although if you see some of the cartoons, then yes, it does. It's very sad.
There's a Rick and Morty episode about that.
So, of course, but no, Pluto also apparently orbits the sun at on a different plane than all the other planets.
Oh, okay.
And that's another one of the things. But I brought up Pluto to kind of also circle back to Planet 9, because it's mainly made of things that are frozen like ice. I don't think it's water ice. I forgot what it was. But that means it has a very high albedo. So they thought it was much bigger than it was. And it was around it just happened to be at the time when they looked at it. It was around the right part of space where Planet 9 could have been for the distorted orbits of the other planets. So they're like, that's the planet. And then they looked more into it and they're like, oh, that's just Pluto. At least that's what I've heard. I mean, that could be completely wrong, but
that's for your listeners to find out.
Yeah, exactly. Yeah. Well, all right. Well, I hope that it was fun talking about space for the short amount of time that we did.
Yep, I enjoyed it. Thank you. Yeah. As I said earlier, you got me reading my my PhD thesis, which I haven't picked up in I don't know how many years. It's like, this is really cool, actually.
Trip down memory.
Yeah, it was, and I was thinking, maybe I should do some imaging of some of my dwarfies. So yeah, cool. See, you've inspired me with this podcast. It's good. Yeah, I will.
Yeah. Hopefully, we inspire some watchers as well. Should we wrap it up then? Okay. Well, thank you for tuning in to the first podcast. This is going to be the first one.
Oh, nice. So didn't know that.
Yeah. All right. And I guess the next one will be coming out next week. At the time of listening.
Next week.
Yeah.
Whenever that next week.
Next week at the time of this being released. Yeah. All right. Thank you everyone for watching.
Bye.
Goodbye.